Well, thank you very much, John, and for the opportunity to speak today on a program that began in 2018 for our section, and which is sort of captured in the banner on the left-hand side there, where we're translating observed earthquakes into a probabilistic understanding of the hazard, and then the last step is actually translating it into regulation for buildings and infrastructure. So when we reflect on the last 12 months, some significant earthquakes have occurred in our region. Now, one mentioned by John is the earthquake that occurred in Vanuatu, had a major impact on Port Vila. 14 people died, 265 injured, damage to infrastructure and buildings. Some of those buildings were older, say the bottom left there, an older structure collapsed. But if we look at the top left, that is a more modern building which housed 4 diplomatic missions, and you can see there that it actually collapsed. Half the building had a soft story collapse, which actually impacted directly there the US Embassy. Now, when it comes to the level of shaking there, that was probably less than design level shaking to their current standard. And then more recently, Myanmar, this is the impact on Mandalay. Over 5,000 people killed in Myanmar, 103 killed in Thailand with the collapse of that building, 11,400 injured, 170 bridges either damaged or destroyed. In this instance, as best we could estimate, above design level if they'd used the latest understanding of hazard in a modern code. Now, when we look at the damage to the buildings, we notice that some of these buildings are quite modern. And looking at the bottom left there, we see catastrophic collapse of apartment buildings there. And in this level of shaking, you would not expect that outcome. You don't want to have a mass loss of life. And looking in the background, you can see that other buildings didn't catastrophically collapse as those in the foreground, indicating that not all buildings are created equal. But it does raise questions when we look on those 2 events that occurred in our region. Well, was the hazard not well understood? Was the hazard not incorporated into the building standards, the manuals being used for bridge design? What about the legislation? Did the legislation call up these standards? The building officials, were they able to enforce them? What about the building professionals? Were they competent when it comes to seismic design? And what about the tertiary institutions training the next generation of architects, engineers? Do they have the resources to actually educate these ones? Well, in these areas, I'd like to describe a journey that we've had in Papua New Guinea that has sought to address that. When we think of those particular countries, it might be that 1 or 2 elements of that were missing. Perhaps most of them were missing, but what we've endeavoured to do here is help them through all aspects of that. So I'm going to begin by talking about the motivation, which has been a new seismic hazard assessment, and then looking at the implications for building regulation, assessing the adequacy of building regulation in the light of the new hazard assessment, engaging with the stakeholders to assess what they need, the development of an interim amendment, and in turn, delivery of new science to professionals that will use it. And then finally, on the legislation side, helping the PNG government revise their legislation to mandate the development of a new standard, and also how that will be influenced by a new loading standard in New Zealand that is soon to be published over there. And then moving on to bridges. Again, assessment of the adequacy of bridge design, engaging with the stakeholders, developing a new updated manual, and then delivering of this new seismic science in a form that can be used by professionals, bridge engineers, geotechnical engineers, and asset managers. And then finally, to sort of lift up this journey to a more strategic level as to what it means for PNG when it comes to resilient infrastructure, and also for other nations in our region. And in doing that, I'd like to acknowledge the contributions to this program of work. DFAT, to begin with, that funded it, and also provided stakeholder liaison in Papua New Guinea. There's been 2 PNG technical review committees set up by the Standards Organisation and the Department of Works to review the outcomes of this work. We've worked with specialist engineering consultants, notably Becker in New Zealand and King Consultants, but also with assistance from Select Consultants here in Canberra. And then the staff here at Geoscience Australia that have contributed, Hadi and Phil, in the hazard itself that has fed into this work, and then others that have helped in developing these documents. And also I'd like to acknowledge the contributions of key ones in corporate, Leila Feta, when it came to the formatting of these rather large documents, and James Cropper, who was instrumental in developing a whole suite of professional development lectures, which I'll describe in due course. So why do we have earthquakes in Papua New Guinea? Well, we all know about this, tectonic plates, the Earth's crust. These are the primary tectonic plates. And when we look at Papua New Guinea is astride the Pacific plate and the Australian plate. But when we look at that plate boundary environment, it's much more complex than that. At the top right, we've got the Pacific plate, bottom left, the Australian plate, AU. But in that region between, there are 10 other plates and microplates that are being stressed by tectonic movement. And that tectonic movement we can see right here at Geoscience Australia with our GNSS stations, the tuned antenna we have. More recently, we can actually observe tectonic movement every year. And looking at the movement that we observe here, over in Karratha, Western Australia, moving on average at 70 millimetres per year, and here in Canberra, 58 millimetres per year. But where we're moving into Papua New Guinea. We're into that rather complex plate boundary region, and that causes relative movement between all of these plates and microplates. And this is work by Richard Stanway, who has been doing geodetic work looking at the movement of monuments in PNG. Now, this relative movement and the stressing that occurs in these plates generates earthquakes. And this is the catalogue of earthquakes assembled by Hadi and Phil, some 40,000 events, and you can see that where these earthquakes are occurring and how large these earthquakes are basically following the boundaries of these plates, as well as earthquakes occurring within the plates due to the crustal stressing, and hence we're getting shallow active crustal earthquakes as well. Now, all of that has been rolled into a new assessment of bedrock hazard. Another DFAT-funded collaboration that preceded this work between Geoscience Australia and the PNG government, the Port Moresby Geophysical Observatory. The initial assessment published in 2016, then following peer review, then published in 2019 as PSHA 19. And what do we notice? Well, we notice that the bedrock hazard, and this is expressed as the 10% chance of exceedance in 50 years, which is a very useful reference likelihood for building regulation and infrastructure regulation. And we see that the hazard varies across the country. So we've got higher hazard around New Britain. We've got that major subduction zone taking place underneath New Britain. We can see the high hazard in Lae. We can also see the Southern Highlands thrust fault region. Now, what is of interest is to look at, well, how seismically active is Papua New Guinea compared to other countries that we tend to associate with high hazard and risk. Well, here's a list of countries. We associate all of those with high hazard in these cities. Some of them have experienced major earthquakes, like San Francisco. Where does PNG sit? Well, for Lae, based on PSHA 19, its bedrock hazard is 0.77 G, only exceeded by Wellington based on the latest probabilistic seismic hazard assessment done in New Zealand. But further work is being done since PSHA 19. So this is a study of the earthquake hazard and risk in Lae. Lae, the second largest city, major implications for economic activity in the country, major port, the largest port when it comes to throughput of economic activity. And so through a further collaboration, a better understanding has been developed of the bedrock hazard under Lae, and now the assessment is as high as 1.02 G, so 32% higher. Takes out Wellington, okay? So we're dealing with a country that has high hazard, very high hazard, in parts of the country. But when we think of the building regulations and the manuals or regulations for infrastructure design, What are we trying to achieve? Well, what we're trying to do is we're trying to achieve a compatibility with the hazard, which is spatially variable and will be influenced by overlying soils, such that the vulnerability or the resilience of that infrastructure will meet societal expectations, whether it comes to loss of life, which is a major focus, but amenity or less directly economic loss. Now, just what is societally acceptable is based on the importance of the building. So if it's an agricultural shed, very limited human exposure, the importance is lower. Whereas if it's a hospital with post-disaster function and has operating theatres, critical care facilities, then the importance is much higher. We expect a higher level of performance. So when we look at the building regulations in Papua New Guinea, these are the ones that are actually currently called up in the legislation, developed in the 1980s. This was an initiative funded by the PNG, the Australian government. It includes earthquake as well as other environmental hazards such as the wind. And at the time, it was an adaptation of the standards we had right here in Australia, but with the introduction of seismic design provisions. And that was done by consultant Becker Carter Hollings and Ferner, now Becker in New Zealand, and it covered a whole range of construction materials too. However, over 40 years on, unchanged. So what we're focusing on today is part 4, which is the earthquake loading standard. How adequate is the present standard in meeting the societal expectations of infrastructure in PNG? Well, if we look at the standard, the actual hazard across the country in the current standard, and also the bridge standard has the same zonation map, it's by zone. So we've got zone 1 being the highest, so that captures a large part of New Britain, New Ireland, Bougainville, and then as we come across the country, progressively zone 2, zone 3, zone 4, lower and lower hazard for design. And if we compare that to the new understanding in PSHA 19, what do we notice? Well, we notice, for example, that the high hazard in the Ley region, the Huon Peninsula, is not reflected in the zonation map. So zone 2 rather than zone 1 for Ley. We also have the Southern Highlands Thrust Fault region there, where there was a major earthquake in February 2018, which killed 160 people, and then 40 people perished in the aftershocks. Well, that's not featured, that's only zone 3. So we've got an issue spatially where we're defining where the hazard is high, but we also have an issue when it comes to the absolute value of design hazard. Now, to help us consider that, what we did was we had a look at the range of buildings built in Papua New Guinea. Now, all of these buildings are actually buildings existing in Port Moresby, from short, stiff structures, say a short period of 0.2 seconds, progressively taller and longer periods until we get to the tallest building in the country. And what is a significant parameter for these when it comes to assessing adequacy is what we call the natural period of the first mode of vibration. So to help you explain what that is, if you could get hold of one of these buildings and you pulled it to one side and you released it, that would be the time it would take for it to oscillate and come back to where we released it, with all floors moving in the same direction. The natural period of the first mode of vibration, T1, and that's been a key reference value for assessing the adequacy of the design. And to do that, we looked at a range of communities across the country and virtually placed these building types to see whether we would be under-designing or whether we would be over-designing these buildings. So here is a summary of all those communities, 27 of them. Across the top there, we have the natural periods of those taller and taller buildings. Orange indicates under-design by at least 10%. Blue indicates over-design by at least 50%, where what we're doing is we're over-investing in the seismic resilience of the building. And what do we notice? Well, first of all, we notice that typically shorter period buildings across the country are being under-designed. Most buildings in PNG are of those natural periods. The taller buildings over here pretty much only exist in Port Moresby, and there's not a large number of them. And then when we look at the major cities of Ley and Port Moresby, what do we notice? Well, we notice that for lay, we're under-designing a short period building by a factor of 5, and in Port Moresby it would be a factor of 3, and if we go down to Milne Bay Province, Alatau is a factor of 7. So very significant under-design. So with this review done, we actually took that back to the stakeholders. So we had 2 workshops in Port Moresby to engage with a whole range of stakeholders that use or are influenced by the application of the building regulations to determine, well, what are their needs going forward. So from that stakeholder engagement, there was a recognition that really all the standards needed updating. They were 40 plus years old. That in updating them, what would be very good would be to actually keep Australasian consistency. So between Australia and New Zealand, we have common structural design standards. The only area where they differ a little is when it comes to earthquake loading. So compatibility to Australasian design practice. And then a 2-stage approach. The first stage to actually provide some interim guidance so that you avoid the under-design, and then as a second stage, a new suite of structural design standards for Papua New Guinea. And the aim not only being to address the under-design, but also to move design practice closer to present practice in Australia and New Zealand, which represents best practice around the world because things have changed over a 40-year period. So I'm going to look at 3 aspects of what we did to actually take that new hazard and introduce it into an interim amendment that could be used alongside the earthquake loading standard. Now, the first thing was, well, how do we define the hazard across the country? Do we use zones? Now, there was a keen interest with the stakeholders, Department of Works, that managed the legislation to do it with zones, because the legislation describes the hazard in zones, so we'd have to change the legislation if we packaged up the hazard in a different way. So this is work done by Neil Corby, where the very complex varying hazard across the country, he tried to create the 4 zones, ended up with 80 ordinances to define the corners of those zones, being careful not to put a boundary between the zones right through a community where half the town would be designed for one hazard and the rest of the town to a lower hazard. And it just didn't prove to be practical. And then the disadvantage of zones is that the hazard you define for the zone has to be the highest hazard in the whole zone. So it leads to over-design elsewhere in the zone. So in negotiating with the stakeholders, we came up with a zonation map. So this is the zonation map, tabulated the values of bedrock hazard for 45 communities. And then these contours are very useful for buildings outside of those communities, or it might be a bridge, or it might be a reservoir, or it might be some other infrastructure. We can actually determine the bedrock hazard at that location and described by an earthquake hazard factor Z, which is used in Australia and New Zealand. Now, we also wanted to look at how the earthquake hazard for design might be influenced by the seismotectonic setting. Now, to understand what we were looking at there, and Huddy went through and categorised these 27 communities based on the nature of the earthquakes driving the hazard in the community. So if the earthquakes typically are local earthquakes that are contributing most to the hazard, it means that there's a higher frequency content in typical ground motions, which influences the demand for shorter structures versus longer period structures. Whereas, for example, if it's megathrust earthquakes tend to have longer frequency or longer period, lower frequency components, and so that increases the demand for longer period structures. Or we could have communities which are combinations of the two. So we had 4 categories, and these are these 27 communities again. So an example would be Daru. So Daru is coloured in blue in the bottom left. That the hazard there is very much driven by local earthquakes. Whereas if we go to, say, Kimbe, which is in New Britain, which is grey, that's very much dominated by subducting lithosphere underneath New Britain and giving that longer period content, and combinations between the two. So just to illustrate what we're looking at, there's Ley, for example. We've deaggregated the hazard and looked at where the earthquakes contributing to the hazard are located in the percentage contribution to the bedrock hazard. And you can see for lay, it's all very clustered around lay, driven by the local fault systems there and active crustal earthquakes there. Mendi in the Southern Highlands, very similar. Whereas if we go to Kokopo in New Britain, we notice that there's a big contribution from the megathrust underneath the island, but there's a significant contribution from the bottom megathrust under New Britain, and then a significant contribution from New Ireland. So it's a mixed environment. Now, when we look at the demand associated with this, and what you see here is actually the factor that's used for determining the loading, which is the spectral shape factor, along the x-axis. This is the spectral period. We can think of that as the period of the building. So taller buildings are more to the right, and as we expected, the demands are higher where we're looking at megathrust contributions to the ground motion. So the question was, well, do we need to differentiate between the two across the country? So what we found was that if we took the New Zealand spectral factors for a rock site, that's a Class AB rock site, it was a reasonably good envelope of those 27 communities. So those are the 27 communities, and effectively the spectral shape factor for each of those, and we found that that was a reasonable envelope. We adopted that, and then we in turn adopted the spectral shapes for two other soil classes, that's intermediate and soft soil. So what we were doing there, we were actually expanding the range of soil types from 2, because in the present standard, soft and firm, we've now moved from rock to intermediate to soft soil, and then there's guidance there if you're looking at even softer soil sites. So we're better targeting the hazard for design to the local hazard at the site. And then the third thing, just to highlight how we've introduced this new seismological science into the building regulation, is to look at how the design level changes with the rarity of ground motion that would apply to different importance classes of buildings. And so what you see here on the right here is basically a return period factor for all those 27 communities. We assessed what the average one was for a range of return periods of interest for design, and we found that to factor loading for more important structures, we found that the factors in the New Zealand standard ended up being very similar to what we got from PSHA 19. So we've adopted the PSHA 19 influence values, but they are very similar to New Zealand. And we might expect that because both countries are in a very similar seismotectonic setting. So where this comes to play is when we're looking at the importance of the building, which relates to the consequence of failure. So if you've got, for example, a building which has low consequence of failure, low risk to human life, that would be importance level 1. Most buildings sit with importance level 2, but say if it was a hospital with post-disaster function, it would become importance level 4. Or if it's holding hazardous materials that you might not want to be liberated to the public. And then there's even a category 5 by special study, and that might be something of a nuclear nature where there's even greater consequences if there was damage caused by an earthquake. So having identified the importance levels, and the descriptions around those was improved in the interim amendment as opposed to what's in the current standard, it also then gives the engineer how much to factor the loading up, whether he's designing it for ultimate limit state or whether it's a serviceability condition that you're wanting to design for. And then the last thing that we needed to include in the interim amendment was the recognition that the current standard was called up in the legislation. So the minimum requirement was the current standard. So you couldn't take advantage of avoiding over-design. And so this is the flow chart in the interim amendment where what you need to do is you need to assess what you'd have to design using the current standard. This is the more refined, improved assessment of design load, and then you would need to adopt the greatest. So the result has been this. This is the interim amendment. Here's a copy of it right here. It was released by the Minister of Public Works and Highways, the Honorary Sola Mirisim, in July 2023. And then following the launch, the formal launch, we had a series of seminars. So The first seminar directed to structural engineers, the second seminar directed to architects, building officials, and the construction industry was also invited to that second seminar. So you can see the seminar being run there, and from the seminars, because we did a video capture of them, we're able to bring all that video content back, and our media team translated that into 13 professional development lectures for training of those who missed out, and also as a resource for the university as well. So they have been provided back to the stakeholders in PNG. But we had some complications, because if we just go back to those seminars, some missed out. And so there was a request to run the seminar for structural engineers again. We did in April the following year. And what became apparent was, in almost a year, the interim amendment was not being used very much. And the reason being is that for clients, building a building, if it required more investment in the building, they'd rather just stick with what they had to do rather than what ideally they should do. And the problem was that while the interim amendment was a resource, it was not mandated. There was a choice, and that was the choice being exercised. So in discussion with the stakeholders there, and particularly DFAT, we got additional funding because we saw the need to actually develop a new standard for PNG that could be called up in the legislation. So the journey has been from the current standard, the interim amendment, and then rolling those provisions into a new standard, and that has just been reviewed by their technical review committee. And then there's another little complication that's come up most recently, and that is that the New Zealanders are changing their loading standards. So the New Zealand standard was a strong influence to the changes made in the interim amendment and then the new standard for PNG, and they're removing a provision called the equal energy principle. Now, I won't go into all the details of what that is, but the implications of removing that is it reduces the design loading that you need to design for, because with the equal energy principle, what it does is it increases the design load that you need for shorter, stiffer structures, because the benefits of ductility are not as effective in reducing the design loads for the structure. So to illustrate how much difference it makes, if we're looking at a building with 0.7 second natural period, so that's sort of like your 6 or 8 story building, and you go to shorter and stiffer structures, the design load goes up to, say, by 75% for a 0.3 second structure, which is the more common structure in PNG. So there's quite an impasse there. So knowing that the New Zealanders are about to remove it, we discussed that with the stakeholders and agreed that we would further amend the 2025 standard and remove that. So while PNG is having to design for higher hazard overall, they're not having this impasse on design, which is now being removed. So let's just summarise the journey. What did we do? Well, we assessed the earthquake design issues. We engaged with the stakeholders as to their needs. The interim amendment was developed to avoid under-design. We delivered professional development seminars to engineers, architects and building officials in country. From those, developed a suite of video lectures for continued professional development training. We've assisted with the updating of legislation and developed a new earthquake loading standard. And looking ahead, the journey continues. The new standard is about to be published, so in fact it may well be published this month. The legislation needs to be enacted, and there's a little bit more we need to do for the Department of Works for them to finalise that. We're waiting on them at the moment. The new standard will be subsequently amended to reflect where the New Zealand standard is going. So that's out for public comment. It's not the standard that's called up in their building regulations, but will be. So we're anticipating that. We've translated the interim amendment to a new standard. And looking ahead further, what the Department of Works have indicated is that they would like new standards for the other loadings, so the environmental hazard of wind and also for dead and live loading. And then ultimately, with a Pacific focus, what would be a great development of this work is to develop regionally consistent standards that can be used in any of our Pacific Island nations by introducing the hazard relevant to them, and also taking into account any local variance when it comes to the nature of their building stock. But what about bridges? Well, not long after the publishing of the standards in 1982, 1985, a bridge manual was developed, and that involved Becker, Carter, Hollings and Ferner at the time. It wasn't a standard, it was a manual, and it was more than what was in a loading standard. Yes, it included earthquake loadings, but it also had provisions on structural design of elements. It had very extensive geotechnical guidance for investigation and design. It was tailored to 3 common bridge types in PNG, and particularly provided information on this type of bridge that you see on the bottom right. It's called a Bailey Bridge. Now, originally developed for military purposes, used in Australia and New Zealand as a temporary bridge. In Papua New Guinea, these are installed as a permanent bridge. So in making these seismically resilient, there was a need for special detailing. That was provided. And also it was more educational. It provided broader information on training engineers about earthquake engineering design principles. But it's 40 years old today. Well, not today, this year. And only available in paper copy and out of print. So that really needed attention too. And so what we did was we did a similar exercise as we did with buildings. We looked at the range of bridges built in PNG, their natural periods. We looked at the same communities, but with these different periods of interest. And yes, we found the same problem. We found under design. So if we're looking at, for example, Lay and Port Moresby, for a shorter, stiffer bridge, you're looking at an under design by a factor of 3, and Port Moresby would be about under design by 30%. So in a similar way, we took that to the stakeholders, now a much smaller group because we're dealing with just no architects at these workshops, and got their view as to what did they need given what we've learnt about the adequacy of design in the country. So we had 2 workshops there, and what we got from that was that they wanted to still continue to use the Australian bridge standard. So it's AS 5100. They wanted to use that for all aspects of bridge design, but earthquake design. So they wanted their manual updated for that purpose. They wanted alignment as best possible with Australasian practice in Australia and New Zealand. Some things were a lighter touch, other things had a major revision. There was agreement on certain key design parameters, such as bridge design life, for example. So here in Australia, we design for a bridge design life of 100 years. In New Zealand, it's 50 years. 50 years was adopted for PNG. And they also identified the need for 2 tailored seminars, one to bridge engineers, geotechnical engineers involved with the design of bridges, and they also saw the need for a more tailored seminar for provincial engineers in the 22 provinces that manage the assets, that have a role after an earthquake in terms of assessing whether bridges can be used after an earthquake. So that led to some seminars that I'll tell you about in a moment. So this was been the result. So this was the version of the bridge manual that was used at the seminars, the draft 2. Same structure as the original manual, refresh of figures and photographs. The new hazard was incorporated using the design methodology in the New Zealand Transit New Zealand manuals. The structural provisions were updated, but there was a very extensive revision of the geotechnical. And again, more than hazard, it actually moved design practice closer to Australasian practice. And the manual now is being reviewed internally, so we would expect that to be available for the PNG government to publish probably in a couple of months' time. So there's been a lot of work doing that. But there was some additional work that was done from the hazard side, and that's to deal with the third bullet point there. There was other hazard metrics required to support liquefaction assessment. And so what we needed to do was to provide the mean magnitude for the hazard at that location and for a return period. Now, if you don't want, we all know what liquefaction is, but there's some examples of it from Christchurch. Basically, you've got poorly consolidated, saturated layers, and then with sustained shaking, intense shaking, they actually lose their strength and liquefy, and we see the consequences for your car, but also the consequences is for roads. So that needs to be assessed when it comes to the design of bridges. And so what that required was actually taking PNG, looking at 230 locations in a grid across the country, deaggregating the hazard, assessing the mean magnitude, and the mean magnitude then would give an indication of duration of shaking in assessing liquefaction. So liquefaction is duration of shaking and peak ground acceleration are the two parameters that go into the assessment. So those were new products for us to develop, and this is straight out of the manual you see there on the left. Now, interestingly, we had the opportunity of linking the geotechnical liquefaction assessment provisions in the bridge manual to the building standard, because we were working on both of those, so we were able to cross-reference this information in the new standard, which is new because the New Zealand standard doesn't actually cross-reference it, but we're able to do it because if you're designing a building, you have equal issues with foundations and liquefaction beneath buildings, and so this is a resource also for building design. So that was followed by professional development seminars run this year in May. The first one directed to bridge engineers and to geotechnical engineers, and the second one was directed to the provincial engineers. And from them, altogether 23 professional development lectures have been developed and are under review, so they'll be provided to the stakeholders in due course. So what is the journey? We've started off with the assessment of the earthquake design issues for bridges, engaged with the stakeholders to assess what they need. We've updated the bridge manual. We've aligned with anticipated future New Zealand design practice. So that brings us back to that equal energy principle. For bridge design in New Zealand, the Transit New Zealand manuals have the equal energy provision, that impost in them. In consulting with the engineers in New Zealand, they were very sure that in due course, once the building design standard removed it, then Transit New Zealand would remove it from the bridge manual. So we've anticipated that change. So in that sense, the bridge manual is ahead of the Transit New Zealand design manuals in New Zealand. We've provided professional training seminars to bridge engineers, geotechnical engineers, provincial engineers, and then these lectures have been developed and will be shared back to the stakeholders in PNG. But let's lift up the discussion to a more strategic view of the importance of resilience in our infrastructure. Now, in the introduction or preamble to the new manual, the Secretary of Department of Works, that's Gibson Halimba, made the following statement. He said that this revised manual marks a transformative step forward in engineering resilience and safety for Papua New Guinea's transport infrastructure. May it serve as a practical and reliable guide as we continue to build a safer, stronger, and more connected Papua New Guinea. And at the end of the second seminar that we ran on bridge design, he provided a concluding address on the significance of the work. And what I'd like to do is play that for you, and we'll just identify some key things that he said.
The revised earthquake engineering guidelines and specifications we have worked on will now guide our bridge designs to better reflect our local seismic conditions, terrain and geotechnical realities. These standards will also align PNG with global best practice while retaining our national context and our environmental challenges. The initiative directly supports our national development goals under the Vision 2050, our National Transport Strategy Plan, our Connect PNG investment program that the government is supporting. And so, because resilient infrastructure is not an option, it's a cornerstone of sustainable and inclusive development.
So if we just analyse some of the things he said there, some key words. He said that the new manual reflects local seismic conditions, and it does. It aligns PNG with global best practice, it does. And then more strategically, it supports their national development goals, that resilient infrastructure is not an option, it's a cornerstone of sustainable and inclusive development. The very economy of a country is influenced by the resilience of the infrastructure it depends upon. And interestingly, after the seminars, we got to meet with the Secretary of the Department there, and he expressed the wish that this would be augmented in time to include guidance not just for bridges, but also for ports, for electricity infrastructure and for water treatment facilities as a series of appendices. So that's something, the best road for doing that needs to be negotiated, but there is a synergy with work that we're about to commence for the Australian government here. And that's to do with the Australian Infrastructure Financing Facility for the Pacific. And it was established in July 2019. The goals of this infrastructure facility are listed there from the website, the DFAT website. But it's really to support quality, resilient, and inclusive economic infrastructure. So this facility has actually come to GA to help with these projects that they're financing in the Pacific, a guidance document that can be used for engineering consultants working on these. And the focus of this initial piece of work is going to be ports. So what we learn from that, and when it comes to best standards and practices for port facilities, we can then translate that potentially into an augmentation of the manual for bridges or some other means of conveying that design information to design professionals in PNG. So let's see what we've achieved for Papua New Guinea. We could ask the question, going back to the outcomes in Vanuatu and Myanmar, is the earthquake hazard reliably known? Yes, it is. Do design standards reflect that hazard? Yes, they do. Are the standards mandated in the legislation? Soon. Not too far away there. Are the standards enforced by building officials? Yes, they are. Are local design professionals trained and supported in the use of these design standards and practices? Yes, they are. And are there resources available that can be used by the university in PNG that trains architects and engineers, which is Lay Technical University, in training the next generation of building professionals? Well, yes, there are those resources available. So in summary, the seismic hazard of PNG has been reassessed by a project led by Geoscience Australia with the PNG government. It's shown that the hazard across PNG is high as you'll find in any plate boundary country. In comparing that new understanding of the hazard to the standards for building design, the manuals for bridge design, it's shown that typically buildings and bridges are being under-designed. PNG stakeholders have identified their needs, a new building standard and an update to their bridge design manual. These have been delivered, they've been launched. Professional development seminars have been delivered or presented, and 36 professional development video lectures have been developed from that with 6 different professional audiences. And looking ahead, future work is in producing commentaries, first of all, to translate the interim amendment to a guide for the new standard, because strictly the interim amendment is looking at the situation where the current standard is in force. So they're not aligned. So there's a piece of work that we've identified there. Also, the address of a broader range of infrastructure types, and then an update to other building standards that deal with wind loading. So that's the other key environmental hazard. And if you update the standard for building design, it actually carries over into other infrastructure types. So an update to the wind loading standard for buildings would inform the design of transmission lines and communication towers and the like. And then in final comment is that this multi-year program has translated new seismic science to design practice, thereby promoting resilient PNG communities and their supporting infrastructure. Thank you. Thank you.